Okay, we're now in part two of this mini lecture on representing mathematical equations and operators as block diagrams. So we're going to look at another example here, which we're going to use a second order ODE. And so by way of example, we're going to look at the mass spring damper, the MSD system. And we derived this set of equations before. We have y double dot plus 2 zeta omega n y dot plus omega n squared y is equal to some omega n squared, u of t. There we go. So I always like to start with the highest derivative when I'm doing this. And so, in other words, start with the y double dot, push that through one integrator, and out comes y dot. Push that through another integrator, and out comes y. And it's important to notice that I'm not really worried about the initial conditions or the limits of the integration and all of this. And we'll get to looking at that when we actually use Simulink. But for now, we can just kind of assume that this is the total integral, right? It's integrating from minus infinity to infinity or something like that. So now we can add the equal sign. And so now add the equals sign. Still getting used to the pen. And the way we can do that is say, all right, well, I've got to have this summation. Put out is that y double dot. And really what I'm doing here is saying that I'm starting with the highest derivative, so I know that y double dot has to be minus 2 zeta omega n y dot minus omega n squared y plus omega n squared u of t. So the summation then is I'm going to add all these signals together. And so I've got y, should be y double dot. Let me clean that up a little bit. Don't connect that. All right. Still getting used to the pen. All right. And hang on. Gotta go to get my pen back. All right. Integrate, and out comes y dot. And now I can feedback both y dot and y through different gains. And so if I take y, this is 2 zeta omega n, and then I push this through omega n squared. And now I can add all these up in the sum junction. So I have to have some minus signs there. And then I need to add in omega n squared there and u of t coming in there. All right, so now I've got a whole block diagram, albeit a little messy, and I can go ahead and clean this up. And there's, in fact, this is one of the tricks for block diagrams, is that there are a lot of different ways to represent this system, and we're going to play with some of this throughout the class. And so one way to do this would be to say, all right, well, let's do the same thing. Let's start with u of t here. So we're going to represent the same mathematical equation. And I've got the sum junction here, and I'll try to be a little neat. And I'll push that through omega n squared. And then go ahead and add that together with some stuff, which we'll get to. And then I've got y double dot there. I go ahead and integrate again. Out comes y. I've got y dot here. And what I do is I feed back y dot through 2 zeta omega n in a block. Feed that through here with a minus sign. And then I take y and feed it all the way back to there with a minus sign. And notice that still represents the same set of differential equations that we had before, because the y and u of t are both being, once I add them together with a minus sign, multiply both of them by omega n squared, then add that whole thing to y dot times 2 zeta omega n with a minus sign, and that gives me y double dot. There's another way to do this, is to say, all right, I'll start with the input, u of t, and pull the sum junction there, take that through, feed it to the first integrator, feed that to the second integrator, and then out comes y. And I can take, so this is y double dot, y dot, and I can take y dot, push it through the gain 2 zeta omega n, pull that signal over to here to a sum junction with a minus sign, take y, feed that through omega n squared. Go ahead and push that through there with a minus sign, and then push that whole summation up to here. And now that just has a plus sign. Oh, everybody notice I did make one little mistake, and you can always go through and try to collapse this down and to make sure you've got the right equation. But notice omega u of t is not multiplied by omega n squared. So I can go ahead and get all that. Let's see. And sorry guys, still working on. There you go. All right. Take u of t, feed that through omega n squared, and then add that in that way. And I'm good. So you might think one of these looks better or cleaner or makes more sense than the other, and that's going to be basically up to you as the engineer to decide what you're comfortable with. Notice that we said that u of t, when we went ahead and derived the second order mass MSD equation, we said u of t was a displacement function, and then y, notice this is y of t here, I'm leaving that off, but that's the actual displacement of the spring. So this whole block diagram represents the system from a controls point of view, as here's an input, a displacement function, and here's the actual displacement of the system. So we can think of u of t as being the input, y of t as being the output, and everything in between, this whole thing right through there, I could put a box around that and call that the plant. All right, and we've talked about what the plant is and what it represents. And so what we could do is, if we could collapse this down into one thing, which we'll look at how to do that, we could just have one block that represents the plant, and we could have an input u of t and an output y of t. So in this way, if I collapse this down to a single block, it represents something like a subsystem or a function from, say, MATLAB that as it goes along, if I give it an input u, I get an output y. So there's also a similarity here to MATLAB function programming. All right, or really function programming in any language, but we are familiar with MATLAB. So not only do these blocks represent mathematical equations and operators, but they also represent the idea of a function in a program. And that's going to be useful for us when we look into Simulink. Simulink. All right. Which is part of MATLAB. All right, so that sums up everything that we're going to talk about with block diagrams today. We'll do more of this throughout the class, and we'll learn how to collapse these down, or in other words, combine feedback loops so that we can look at overall, make basically single blocks out of this. And the next concept that this is going to take us to, which is really embedded here in the plant, is called the transfer function. And we haven't seen what that is yet, but we're going to read about it, and it's going to be useful for us in the context of putting together block diagrams.